Hello everyone, so today we are going to study about DNA replication. So what is DNA replication? Just basic, we understand that it is process of division of DNA to produce multiple copies of DNA, right? It takes place generally in interphase S phase of cell division, right? Now, what we have to understand is that DNA replication takes place by three processes. Takes place by three different methods. First method being first, number one, being the conservative DNA replication. Second model being dispersive DNA replication method, and third model being the semi-conservative DNA replication, right? Replication. Now, simply to understand what is conservative method of DNA replication, right? So where the parent's DNA is consort, daughter DNA do not get any parental DNA. Simply, if you want to see this, then if this is the parent DNA, then after replication, the daughter DNA will be formed in this fashion, right? 5 to 3, 3 to 5. Then we will have another complete whole set of DNA. 3, 3 to 5. Now this is the daughter DNA, while this is the parental DNA after replication, right? Now then we come to dispersive method of DNA replication. In this, what happens is the parent DNA gets mixed with the DAU GSC daughter DNA. Simply understand that. Now in this, what happens is, suppose this is the parent's DNA, right? 5 to 3 and 3 to 5, right? So after replication, what will happen is that like this structure will be formed. Now this red one is the DAU daughter's DNA strand, while the yellow one is the parental DNA strand, right? Okay, this is the dispersive method. Now we come to semi-conservative method of DNA replication. Now we have to understand that this one is the most common type, common type, right? And this, what happens is the daughter DNA will have one PAREN parental and one new strand formed during replication, right? Now let's go more deep into the semi-conservative method of DNA replication. METS method of semi-conservative DNA replication. So just to understand is that in this process, if this be the parental DNA, right, then after replication we will have one parental DNA and another strand with the daughter DNA, right? What will this be? This will be the DAU GST, daughter DNA strand, and this will be the parental parental DNA strand, right? And they're always anti-parallel to each other, meaning if this goes from 5 to 3 minute direction, then it will go from 3 minute to 5 minute directions. Let me write here, right? Anti-parallel to each other, anti-parallel to each other, right? Now let's go. Let's understand. For DNA to replicate, we need various enzymes are needed. For examples, let me write in bright color, right? For example, DNA A protein, helicase enzyme, you can say, because enzymes are also proteins, you know that, right? Then SSB proteins, then DNA topoisomerases, then what we need is DNA polymerase, polymerase, right? And also we need an RNA primer. Now energy source, we also need a few energy sources, right? Energy source is ATP, GTP, DATP, DZTP, then DCTP, right? And then DTTP. Why? Because there is no uracil present in DNA, hence only these four will take part in the formation of DNA, right? Now, why D? Because D means deoxynucleotide. Deoxy, NuCl, TI, D is deoxynucleotides. We have to remember this, right? Now, for initiation, for INI, okay, we will have a DNA strand, right? Let's make a DNA strand. This be a strand of DNA. This be the nucleotides that are attached to the strands of DNA, right? let this all be those strands. Okay. Now, A means adenine will pair with thymine. Similarly, cytosine will pair with guanine. Similarly, A, T, G, C, right? Now, A and T will have double bond in them, while C and G will have triple bond. Let me do it with more conviction, right? This double bond, and then they will have triple bond. Now, what kind of bond are these is the main question. These are hydrogen bonds, right? Hydrogen bonds. Now, obviously, for DNA replication, these two strands must be separated to make, the complementary DNA strand. So, this bond must be broken, right? Must be broken. BRKN broken. Now, what helps in breaking these bonds is helped by, number one, DNA A protein. Then number two, by helicase, right? Now, what happens is, suppose this side, this is a site. Let's take an example. Okay? Suppose this is a site where the DNA replication can occur by the breaking of the bond that is hydrogen bond that is present at this site in between the nucleotide pair, right? So let this site be called as OE site. OE means origin, let's suppose, right? Then what happens is this DNA A protein initially break some bonds here, break some bonds on OE site, right? Then what happens is the helicase goes and binds to the center, goes and binds or be placed between two strands, cleaving the hydrogen bonds. Now, the important thing to understand is that this cleaving can take place in both the direction. That means by directional cleaving of bonds for DNA replication, right? Then what will happen is, now after all these things happen, right, now there will be the formation of replication fork. There will be the FOR, formation of replication fork. FOR, okay, formation of the replication fork. Now, how is this formed and what does it look like? Let me give you an example, right? So here we have our DNA strands, right? Here we have our DNA strands. Now, in between those strands are placed the nucleotides, right? A, T, G, C, T, A, C, G, suppose, right? And we have hydrogen bonds between them. A and T will have double hydrogen bonds, while G and C will have triple hydrogen bonds, triple bond between them, right? The three. And this DNA strand can be supercoiled. Supercoiling can happen, obviously, in any part of DNA, right? So, what happens is this enzyme, let's take an example, this enzyme, right? Let this enzyme be called as helicase. This is HELICASE, helicase. This will go on breaking, this will break these bonds, right? This will break these bonds and open up a larger replication fork as the DNA replication process goes on, right? Because we need to add complementary DNA nucleotides to each of these nucleotides, right? Each of these nucleotides for making a new strand of DNA. Now, as these DNA strands keep on opening, they have the tendency to again reattach to each other by forming this hydrogen bond, again, right? So what happens? There is another protein called, which I mentioned before, known as the SSB proteins, right? These are the SSB proteins, right, on both the sides, right? Suppose these are what are these? These are SSB proteins. PRP. SSB. What does SSB mean? It means single stranded binding protein. Okay, so this will help to prevent the formation, prevent formation of bonds again. Right? Now what happens is the elongation phase comes. In the elongation phase of DNA replication, obviously what we need to do is make a new strand of DNA, right? So that is carried out by an enzyme known as DNA polymerase. But DNA polymerase itself do not have the ability to start the replicative process. So there we need something known as a primer. What is this? This is a RNA primer, right? So let this strand of DNA be from 3-minute to 5-minute direction, and this from 5-minute to 3-minute direction, right? Now this is RNA primer, right? So this RNA primer always runs from 3 to 5-minute direction. Now what we have to understand is that the DNA polymerase, our hero, binds to this 5-minute in of RNA primer. What is this? This is DNA polymerase DNA polymerase. Now if I have to add a note, then I will add that it do not have ability to add, especially DNA polymerase 3, okay? Now it add new nucleotides for making or complementary DNA. Hence, primer is required, right? Now what will happen is that this DNA polymerase will go on adding, right? It will keep on adding new nucleotide pairs like this from the 5-minute in to the 3-minute in of gain, right? So the DNA replication goes on from here, from this point, 5-minute to 3-minute direction, right? Forming a leading strand. What will this be called as? This will be called as a leading strand. Why leading strand? Because there are no any hindrance while making this DNA. It just made this DNA, right? But what happened in this strand is that we have to understand. Let me add one more note, that DNA replication always takes place in 5-minute to 3-minute direction, right? So we have to make the DNA strand in 5-minute to 3-minute direction, right? Now, for that reason, the RNA primer in this 5-minute to 3-minute strand of DNA will be added away from the replication fork, meaning suppose this be the primer, right? So initially the primer will be added here, then again it will be added here, then again it will be added here, and then here, like forming it in 3 to 5, this is 5, again this will be 3-minute direction, this is 5-minute direction, this is 3-minute direction, then 5-minute direction to 5-minute direction, okay? Now, then what will happen is that DNA polymerase will again come, and then attach him to the 5-minute in of these RNA primers, right? And then it will add on nucleotides like this. It will add on nucleotide to this pairs, right? And then, here, what is seen is some segments are formed, right? These segments of DNA fragments are formed here, like this fragment is formed. Again, we have this fragment here. So these fragments, FRAGME, fragments of complementary DNA strand is known as Okazaki fragments, right? Then what happens is these fragments, let me write here clearly, these fragments, FRAG fragments, are later joined by DNA ligase enzyme, right? Ligase means it will ligate, it will join these DNA strands, okay? Now, another thing to understand is that as this strand, which is being formed in fragments, right, there is obviously a hindrance to the DNA polymerase to make the new strand of DNA. So it will be formed later on than the leading strand. Hence, this strand is known as the lagging strand. What is this known as? LAGG, the lagging strand of DNA, right? Yes. Now, as I mentioned this part earlier, this part here, right? This part here is known as a supercoiled, SUP, super, COILE, supercoiled DNA segment, right? So, whenever the helicase will come to this point, right? If this helicase will come to this point, right? Then obviously it will have difficulty in breaking the hydrogen bond because of the supercoiling that is present, isn't it? So, what we need to do is we need to make this strand, both the strands of DNA. That means, let's see here. So, like these are the DNA strands which are supercoiled, right? And in front like this. Suppose helicase came here. Now, obviously it will have difficulty in moving forward, right? If this will be the helicase and this helicase, CEE, right? It will have difficulty in moving forward. So, what I do is if I cut these strands in some points, in few points, right? If I cut these strands, like if I cut it here, if I cut it here, then what will happen is that it will have chance to get converted. To get converted into like strands which are straight, right? And the helicase will pass directly through it, breaking the double bonds in between them, and then we can make the new complementary strands of DNA, right? Now, this supercoiling structure, right, is supercoiling. Get united here. COILI supercoiling is overcome overcome by DNA topoisomerases, right? Now there are two kinds of DNA. What do these topoisomerases do? I already mentioned you. These topoisomerases will cut these strands and then make it straight enough for the helicase to pass between it, right? Now there are two kinds of topoisomerases, topoisomerase 1 and topoisomerase 2, as we study in the semiconductor replication process. Now this topoisomerase 2 in prokaryotes, it's also known as DNA guidase. It has the same function, no any other function, right? Now what does this DNA topoisomerase 1 do is it breaks and ligate only one strand of DNA, while DNA topoisomerase 2 breaks and ligate both the strands of DNA, both in order to reduce the supercoiling. Okay, super COI aligns coiling, right? Then this elongation phase overall will get completed here. Did I write here? Yes, the elongation phase will be completed. Now, how does it end? The DNA replication method, DNA replication ends by removal of primer by DNA polymerase 1. Right? What? DNA polymerase 1. It will remove the primer. Let me write its various functions. Number 1, remove the primer. Number 2, add on new nucleotides. Nucleotides. Number 3, see as it checks the formed strand, newly formed. 6, the newly formed strands for any errors, errors, and then 4 has exonuclease activity. That means if it found any errors, then it will remove that error, removing of the abnormal nucleotide that has been placed, and then it will add on the correct nucleotide to be placed, right? So it has again 5 to 3 minute exonuclease activity, right? So these are different functions of DNA polymerase 1, and then finally it ends by formation of DAU ZST daughter DNA with one parental and one newly formed strands, right? Newly formed strands. So that's it. Thank you. Like and subscribe for more. Ciao.